Hello, in this video we will begin our discussion of buffers by motivating and talking about just what the heck buffers are. Before we do that, though, I should remind you what pKa is. We've talked about this before, this idea that p of anything is equal to the negative log of anything. So for example, pH is equal to the negative log of the concentration of H, or H3O+. And so therefore pKa is the negative log of the Ka. So hydrofluoric acid, its Ka is 7.1 times 10 to the negative fourth. If you take the negative log of that, you get 3.15. And so we use pKa a lot. Here's another example for hydrocyanic acid. And so the nice thing about this is that it puts the range of Ka values into easy to write numbers. So you can talk about, oh, it's 3, 4, 7, and then it matches the pH scale really well. So generally, we describe acids and bases in terms of pKa. You go onto the wiki page, you'll find pKa and not Ka. We will also talk about bases in terms of pKb, and if you add pKa and pKb together, you get 14. Okay, that works. Now, let's move on. Buffer solutions. And so a buffer is defined as a solution of a weak acid and its conjugate base, or a weak base and its conjugate acid. Either one works. Just because there's so many more weak acids in the world than there are weak bases, we tend to use weak acids and their conjugate base as a buffer, but that's not a requirement. And now you also have to have appreciable amounts of both components. So you can't just have a weak acid and, oh, it makes a little bit of conjugate base as part of dissociating. Great, there's a buffer. That doesn't work. You need to have an acid and either add separately its conjugate base to solution, or have an acid and toss a bunch of strong base in there to convert some of the acid to its conjugate base. And then you'll have a buffer. Okay, the big ticket here is that buffers resist changes in pH, and this is critically important in biological processes, as we'll talk about here. And buffers tend to work best when the pH is within about 1 unit of the pKa. And so, treat this as a hard and fast rule if you will. In the real world, nothing's hard and fast. But yeah, so somewhere within a pH unit of the pKa, your system will function as a buffer. So an example, so this would be an acetate buffer. So you have acetic acid. And now if you just look at acetic acid, it'll dissociate and form H3O+ and acetate. And now if you add both the acetic acid and acetates, you have roughly equal parts, then you have a buffer. And now a buffer can't neutralize itself because, well, okay, so it moves this hydrogen from one acetate to the other. Nothing really changed here. So it's not like the acid and the base neutralize each other. In fact, they're both still there. But if you add some external H+ or external OH, then that'll react with the parts of your buffer and not change the pH as much as if you just added the strong acid to water. So why is this important? Okay, I'm going to go with the biochem example. So when you're looking at, say, proteins, which are the workhorses of biology, in effect, they do things, they make reactions happen, they form structural components, they transfer ions or components in and out of membranes, all kinds of things. Your proteins have some sort of charge. And the picture here is showing some protein with a charge. And it's also showing some small molecule in the little blue spot there, showing that your negatively charged small molecule will bind into this positively charged pocket here. Now, this surface charge depends on pH, so if you change the pH, this small molecule won't bind as well, and then this, for example, enzyme won't do what it's supposed to do. All right, so you can look at several of these amino acid side chains. So a protein consists of a peptide backbone and then these side chains that come off. And the hydrophobic side chains, like this one, phenylalanine, will tend to hang out in the inside in aqueous solution. And then the ones that are polar, like the rest of these up here, will tend to point out towards the water in aqueous solution. And so, okay, you have, for example, lysine. And now lysine is a weak base on its own. And so if it's in a solution at a very basic pH, well, then it won't be protonated anymore. Whereas at a lower pH, this will have accepted an H+ and be protonated. And so it's positively charged when it's protonated, but not positively charged appear at higher pH. Similarly for glutamic acid, it's negatively charged at higher pH, but at lower pH, this thing becomes protonated and it's neutral. And so your surface functionality will be very different depending on the pH. So you can imagine it's really important in biological and biochemical systems to stabilize the pH so it doesn't fluctuate wildly. And the trick with pH is if you're around pH 7, your body is pH 7.4, so around pH 7, if you add just a tiny amount of acid, it only takes 10 to the negative 6th molar to change the pH by a whole unit. And that's bad, right? Because you have maybe a couple tenths of a pH unit on either side of 7.4 before you start to feel sick and then die. So the pH really matters here, so we have to stabilize it. So, okay, pure water is not the way to go. But if you have a buffer and you add, say, the same amount of acid to a buffer system, you will not have as big a change in pH. And that's awesome. And then you also have different changes in pH for different quantities of buffer. And this is called buffer capacity, and we'll get to that later. But if you know you're going to need to absorb a lot of added acid or base, then you need a higher concentration of buffer. All right, so some examples. Which one of these is a buffer solution? Take a look. Pause the video if you need to. All right, and so the answer is this top one, the hydrocyanic acid and potassium cyanide. Why you would pick cyanide as a buffer solution, I have no idea. Bad choice. But hey, this is a weak acid, the HCN, and its conjugate base. And so if you add both of them together in roughly equal quantities, then you'll have a buffer. And by roughly equal, I mean within a factor of 10 or so, right? So 1 to 0.1 is in the ballpark of equal. It's better than 1 to 1 times 10 to the negative 6, right? Okay, going down this list, the second one, B, is just the weak acid. The third one is just the weak acid. The fourth one, letter D, is a strong acid and its conjugate base, so that doesn't work. And then the fifth one is a weak acid and then the conjugate base of something else. This is sodium acetate. And so, moral of the story, buffers consist of a weak acid and its conjugate base. Or, less commonly, but still possible, a weak base and its conjugate acid. All right, this one will be your pre-quiz question, so give it a shot. And hopefully after you've already chosen your answer, let me tell you this. So the pKa of hypochlorous acid and sodium hypochlorite, that buffer, okay, so you determine the pKa of the whole thing based on the acid, and that's 7.5. And remember that buffers are effective plus or minus 1 pH unit from the pKa of the acid. So you can use that to figure out how to answer this problem, but hopefully you already did that. All right, that's all I have for this video. Thanks for watching.